All right, the next talk is Russ White, turning to us again, and you will watch him engineer versus complexity.
Engineer versus complexity. So you know how I got this slot, right? Because Tony ran out of other things to talk about and interesting presentation suggestions, so. Filling in the gap. But we have, keeping with our nautical theme, reached the bitter end of the line. We have unwound the line all the way from the capstan, and we have the nice bitter rope left. So, I've been thinking about complexity for a while. Dave Meyer is my inspiration in complexity, if you've ever watched him talk about complexity theory and stuff. Dave's an old friend, and I think he does a great job talking about it. So I started thinking about this and thinking about what to do, and I've been talking about it at NANOG for a couple of years. You may or may not remember some of those talks. I don't know if the clock up here is going weird or something, Tony. It's okay. All right. So I'm going to start with a little bit of background. If you haven't seen my other talks on this, or haven't seen Dave Meyer talk about this a little bit, is that first of all, complexity is impossible to solve. This is kind of a Turing curve, but it's placed in 3 dimensions. So you have the plane of the possible, and down there in the bottom corner, here be dragons. There are certain things you cannot do. For instance, the CAP theorem is an instance of this. Consistent, accessible, partitionable, quality, speed, cost, right? You go to your car mechanic and you say, I want it fast and I want the highest quality parts and I want it to be cheap, and he laughs at you. As well he should. So that's kind of the way the world is built. Complexity is impossible to solve. It just happens this way. So complexity is also necessary. So Dave has this thing about robust yet fragile that he talks about. And if you read Bruce Schneier a lot, I don't know if you know who Bruce Schneier is, but he's a big security guy. And I really like Bruce Schneier, and he talks about ossification, and he talks about fragility in security systems, automated security systems. So, but the bottom line is this: there is a realm there in the green where things are robust. As you increase some complexity, the curve typically breaks over and it becomes fragile as you increase complexity more. There's like a sweet spot, a set of engineering possible solutions that are good for good complexity. There's good complexity. And by the way, you notice I haven't defined complexity, and I'm not going to in this talk. If you really want a definition of complexity, I'll point you to a book, and you can look up Dave Meyer's stuff and look up my presentation from last year and the year before at NANOG on this topic, because I only have 30 minutes and complexity takes longer than 30 minutes to define. But anyway, so there's this good complexity and then there's bad complexity. So this is kind of one of those things you deal with. You have to deal with complexity. So does that mean we just abandon all hope? Do we just give up and say, oh no, things are complex, I give up? No, there are 2 ways of approaching complexity. The first is to think through how to manage complexity in design and operations. Now, Dave's presentations tend to be a lot more theoretical. Mine tend to be a little bit more practical on this. I actually wrote a whole book on thinking through how to manage complexity in network design and architecture. So you can go look that up if you want to. That's not what I'm talking about today. What I actually want to talk about is, how do I approach as an engineer complexity? What do I do as an engineer? So after I finished writing the book, this topic occurred to me, and it was too late to go back to Addison Wesley and add another chapter, so it seemed like a good presentation to do. I'd like to see how that works. Anyway, it's kind of cool to think about, as an engineer, metacognitively, what am I doing to manage complexity in my life as a network engineer? And I think about weird things like this. You know, I'm doing a PhD in philosophy, so this is the type of thing that happens to my brain when I'm thinking about engineering problems. So what I want to do is this is my goal, by the way. She's on the wrong side of the goal, and I know it's a bad picture, but it's okay. The point is, I'm looking for my goal. And if you can find a better picture, please, that's fine. That's not copyrighted by someone someplace, somehow. It's difficult to find good pictures. Anyway, what I want to think about is building a meta model. I want to think about how I build models. So I want to think about what is my process or technique to understand or to comprehend or process in my head complexity, a complex system quickly. This is really important for me. And the reason it's important for me is that I don't want to just think about when I meet a new protocol or somebody throws something at me and says, I want to do this new design. As an engineer, one thing I need to be able to do is to quickly process it. I need to grok it. I need to understand it very quickly. Well, what do I do to do that? How does that actually work mentally? So what I want to do is this is kind of not an experimental presentation, but kind of a narrative presentation. And then I'm going to start with 4 common models. I don't really teach the OSI model anymore. I really don't even teach the DoD model when I teach people. I really use the Rhino model. But I'm going to use the DoD model because it illustrates a particular thing about meta models, or about how we build models in our minds as engineers. And then I'm going to use the Rhino model. If you've never heard of the Rhino model, it's really cool. It's a really neat iterative model that I like a lot. I put a URL there if you want to look at it. And I'm going to look at a couple of slides about a traffic flow across a data center. I do this kind of stuff a lot of times where I look at an application and look at how it lays on the fabric and try to understand what it's doing. And then I want to look at ISP fast reroute because it's kind of another example. So what I want to do on each one of these is I want to figure out what these 3 questions about those things. I want to ask why I'm doing this. What questions or what information does this process, modeling this flow or modeling this thing, actually giving me? What answers am I getting out of this? And what is this like? Because I think these are the 3 crucial things that help me understand something quickly. So this is kind of my model. I have why, what, and how, and this is like. Right? These are the things that I'm going to work at. So you're going to find there that I have this state surface optimization thing there. This is something that, again, if you want to read more about this, there's a whole book on it. It's really kind of cool. I have found it extremely, extremely helpful when I look at new protocols and at looking at even simple design things like, should I aggregate here? It comes down to, it's a straight trade-off. This is exactly like quick, cheap, high quality. Okay? If I'm going to optimize more, I'm going to bite the bullet and take more state to be more optimal in my traffic flows. If I'm going to do DevOps, that's a great thing. It's an abstraction and it's a great thing to do DevOps. But what I'm actually doing is I'm creating more interaction surfaces. So I'm actually increasing complexity in some ways to decrease other things in other ways. So this is all about trade-offs, and it's about figuring out where those trade-offs are to build this meta model. So let's look at the layered DoD model. So what am I trying to do? I'm trying to move information between applications, carry information down the stack, across the wire, and back up the stack. You've seen this picture a million times. You may not be familiar with the DoD model. It's essentially the model on which TCP/IP was really based. The OSI model was kind of run in parallel. There's this whole question about who invented what first, but whatever. The OSI model is very, very similar to the DoD model. It's just that the DoD model only has 4 layers, so it's simpler to put on a slide and it's less messy. So that's why I use the DoD model for this illustration. So what I'm doing is as I'm carrying information down the layers, if I think about it, I'm actually thinking about my APIs between the layers. I'm thinking about my application to transport API, my internet to link API on the backside. I'm thinking about my link to link API. And I'm actually thinking about everything as a set of APIs. So what questions am I answering with this model? I'm answering questions about things like, who is responsible to do what? Who knows what about each piece of information? What function does everything perform? I look at that transport layer and I'm like, what does this transport layer do, right? That's the type of things I'm thinking about. It defines my interaction surfaces and it kind of tells me what's going on with my interaction surfaces. Okay, here's a second model that I'm going to use as an example, is Rhino. Now, Rhino is this thing that I think it's Stephen Day came up with, or is it? Yeah, anyway. Dr. Day came up with. It's a really cool idea. It's an iterative model where what you do is you break down and you start thinking about what are the 4 things that a transport protocol does. What I do when I transport data is I have a transportation section. I have to actually transport the data. I multiplex, I handle errors, and I do flow control. Those are the 4 things that any set of protocols do. And What this model does is it teaches us that this is an iterative process. That I do this at layer 2, I do this again at layer 3, and I do this again at the application layer. And if you really think about it, this is actually what you do. That when I do TCP/IP, I actually have certain things that I'm assigning to different layers. So again, what am I looking at? What questions am I asking and answering? Again, I'm assigning responsibility. Who does what to the data? How does each process accomplish its goals? What are my interaction surfaces? So when I build a layered model of a network, I'm kind of thinking about those types of questions. Okay, so here's a data flow example. I did this when I was working at Ericsson when I was talking about some different ideas about how to do mobile data flows in over a data center fabric. So here, just looking at this thing, so a mobile service device queries a DNS server for a service. The packet has to pass through my virtual edge. I have my flows going on here. When I pass through my virtual edge, I've got to think about OSS BSS. I've got to terminate my encryption. I've got to think about other edge services. Maybe I'm doing carrier grade NAT, maybe I'm not. I don't know, whatever those services might happen to be. And I have to think about where each of those functions take place in the network. Is it in a virtual machine? Is it sitting on a router at the data center edge? Is it actually, where's this stuff happening? And why is it happening there? And then I have to think about what does the DNS server do in response? And so I build these traffic flows of what I'm doing. And I build this whole concept of, I'm going to build HTTP sessions, and there's going to be X number of sessions when I hit a web page off my mobile device, and how that's going to interact with my OSS BSS system and DPI and all these other things. So I think about all of this. So now what questions does this ask? This is asking me, this I could actually model as a UML. Because I'm really thinking about state. What state do I need to make happen at any particular point in this traffic flow? I'm actually mapping out state machine here in effect, okay? So, and again, my next thing is optimization. So if I start thinking about where does each thing happen, how do I optimize this flow to make the best use of my data center fabric and of the VMs and compute and storage resources that I have sitting here in this data center? So these are the types of questions I'm asking. Okay, so here's a control plane example. So router A uses the path through B as its primary path to 192.0.20/24. There's a path through C, but it's blocked by the control plane. Why? Because that is a potential loop, and this is what SPF and any sort of depth first search algorithm is going to do, no matter what type of DFS you're playing with, whether it's Dijkstra's SPF or Bauman Ford or Dual or Path Vector. It doesn't matter which one you use. They all do the same thing. They see the alternate path, they think it might be a loop, so they block it off. Great. So I'd like to be able to use C as an alternate path in the case of this link failure. So I can use a loop-free alternate, which allows me actually to reach through the concept of where that potential alternate path is, and I can think about how I can actually do this stuff. Okay, so now I'm modeling something slightly different. Again, I'm thinking about state and state machines and where this stuff happens. And now I'm start thinking about things like, if I do LFAs, how much state am I adding to the system? How often does that state change? Who needs to own that state? And who needs to manage that state when the network topology changes? Okay, so if you ever deal with failure domains, this is the best way. This is my rule of thumb for finding a failure domain is a failure domain is every router that needs to recompute SPF or the best path tree, however it computes the best path, if the topology changes. That's essentially what a failure domain is. So I think about this, I'm start thinking about things like, how much state's going to be added here? Am I adding optimization? Here I'm trading off state against optimization. So now, if I look at these four models I've just went through really, really fast, and I know you're tired, and we're at the bitter end, and all of that, but what things am I looking at in common? Questions about state, surface, and optimization. Again, these are my trade-offs. Now, what are my other questions that are important? By the way, that's a porpoise. Get it? What's my porpoise? Anyway, sorry, it's a really bad joke, but that's what you get when you get me as a speaker. You get bad jokes. So what other questions are important? Why? What is the problem I'm solving here? And are there other problems or solutions similar to this one that I've seen in the past that I can relate to, okay? What am I doing here? I'm building a mental model of how I can think about a problem in relationship to standard or solid engineering principles and try to understand what these do. So the why question is so important because it's an abstractor, right? I want to look at stuff that I need to look at to solve the problem at hand. It closes off rabbit trails. I'm in the middle of troubleshooting a DNS problem and somebody says to me, so why does the ISIS develop or elect a DIS? That's a really good question, but it has nothing to do with DNS, right? The why question, what problem am I trying to solve right now, by asking why closes off rabbit trails. This is a form of abstraction, mental abstraction is what I'm doing here. It connects the technical to the business. If I can't explain why I'm doing it, maybe I shouldn't be doing it, right? So there's this whole why thing going on here. So this is an important question because it abstracts, it forces me to abstract, and it connects my technical to my business. What is this like? So for instance, finding the shortest path. What are my common solutions? SPF, path vector, Bellman forward, and dual. Those are the ones everybody's familiar with. I'll give you the protocols if you don't know them. SPF is, of course, ISIS, no SPF. Path vector is BGP. Bellman forward is RIP, may it rest in peace. And dual is the edge ERP, which is actually not the same as Bellman forward, but a lot of people think it is. But it is slightly different, shortest path algorithm. So these are all DFS. So common problems with the solution. If I look at something and I say, you're using SPF, you're using Dijkstra to solve the shortest path first problem, I don't care what protocol it is, what's a common problem with SPF? Microloops. Anytime I see somebody using Dijkstra SPF to solve a problem, even if it's not Dijkstra, if it's shortest path first, I assume there's microloops in the solution. How am I dealing with it? Because this is the way algorithmically SPF works. Path vector, slow convergence, inconsistent state. BGP has wedgies because it's a policy distribution protocol. Tony P had a really good statement for it last night. Can't remember what it was. But BGP is basically a way to describe agreed upon peering relationships that happens to have a shortest path algorithm built into it. Okay? So when you describe peering relationships, what are you getting? You get wedgies because nobody's policy matches. So of course those are reflected in the protocol. That's okay. Bellman forward, slow convergence. You get feedback loops from Bellman forward. Feedback loop in Bellman forward that's classic is a spanning tree protocol failure through a crash because the spanning tree, the Bellman forward process allows a loop for a moment, a micro loop that then causes the control plane to fail. This is a feedback loop. That's exactly what this is. Dual, what do I get during convergence and loop is I have feedback loop problems and I drop packets during convergence. I don't have micro loops with the edge ERP. I actually drop packets. It's just a trade-off, right? So now I can think about this. If somebody tells me I'm doing something and I look at it and I recognize they're using SPF, I know what kind of problems to look for. That's a very good mental tool to have in your tool belt. Distributing data, right? Think about things, how do I distribute data? Flooding, multicast, unicast. Again, these all have the same sorts. They have their own problems. Everything is a trade-off here. Reliable data connection or transmission, right? I can do forward correction. I can do data retransmit. I didn't detect and retransmit. I didn't do all the possibilities here. But nonetheless, you can start seeing the pattern. If I can take a particular new thing, I can relate it to something that's old that I know, and I can understand what problems I had in that old thing. I can now know what questions to ask about the new thing to know where the problems are. It's a pretty straightforward process. Okay, why? Here again, what problem am I solving? It narrows my view. Don't boil the ocean. This is my abstraction layer. What and how? Now I'm looking at state, surface, and optimization. These are my trade-offs. If I'm seeing better optimal traffic flows, if somebody brings me a solution to a design problem and says this is going to optimize my data flows, I need to ask, what is it doing to my interaction surfaces? What is it doing to my state? I must be adding state or an interaction surface someplace. I've got to be, because I can't get better optimization without doing one of those two things, right? So I know now what questions I need to be asking, which is kind of cool. This is like, has this problem been solved before? How was it solved, and what were the problems in solving the problem before? I should be able to directly relate these things. So this is a meta model to understanding complex systems quickly. I really like this. I've discovered that since I actually wrote this down and started thinking about it and trying to understand it, that it's actually implicit in a lot of what we do as engineers. It's just not, we just don't make it explicit, but this is kind of what we do. So I think it's really, really, really cool. Build an abstract model by asking the right questions. So the biggest issue with the abstractions, with the why question, is abstractions leak, right? Linsky's law of leaky abstractions, right? Abstractions leak. And so, for instance, aggregation leaks. If I change the metric, or if the A to B link fails, I'm not going to go through this whole thing, but you know, if your metric for your aggregate is dependent on a component that fails, the metric for the aggregate changes. Hence, the abstraction of the aggregate has now leaked through that there was a topology change behind it, right? This is a leaky abstraction. TCP retransmissions are, in a sense, a leaky abstraction. I'm looking at lower level stuff going on. I see a Q drop, which causes a failure in TCP. I'm actually leaking the abstraction of what appears to me to be a point-to-point connection, and I'm actually seeing stuff from underneath that show up in my TCP. Embedded IP addresses are my favorite leaky abstractions, by the way. We embed IP addresses in all sorts of things, and it really drives me a little bit nuts. But anyway, abstractions hide things, right? So this means you don't understand the system in detail as well as you'd like, but you can't build complex systems without abstractions. It's just the way it works. So the nice thing I've discovered is that the more models I build about something, the better I understand it. The more ways I look at something. If I understand the TCP IP stack from the OSI model, the DoD model, and the RINA model, it actually helps me understand what's going on a lot better. Because now I have 3 models to wrap around this concept. So, again, very, very simple. Why? State, surface, and optimization, what and how, and then what is this like? These 3 questions, if you just think about these 3 questions, it's a really useful way, I'm finding myself, to nail down the complexity from an engineering perspective, from my perspective, to like conquer complexity when I see it. I see something that's really complex. If I just run this process and I think, what problem am I solving? Where's my state? Where's my surface? Where's my optimization? What am I optimizing for? At what cost on my state and surface? And state means both speed and amount. And then what is this like? Where have I seen this before? This smells like what? That I've seen in my past. And so I get past that, and I actually find that this is a lot easier for me to deal with. Hey, I got the dreaded blank slide, Tony. So that's it. So if anybody has questions, I am russ@linkedin.com. I blog at Packet Pushers if you don't know what that is. I blog at my own blog. You can find a link to it on my LinkedIn profile. And I'm always hanging around if you want to send me an email or jump on Slack and send me a question or whatever. So that's it.